Hello, my name is Nathan. I'm here with Aman, Judd, Saish, Matthew, and Ty. We all make up the team at Archimedes Health, and today we're going to go over our final design of our accessible weight training project. So before we began designing, we wanted to come up with a problem statement, something that needed to be solved, and to go from there and decide what we could design to solve that specific problem. So our motivation was that so access to effective weightlifting equipment is not always accessible to everyone. There's high membership costs, depending on where you're located. There's inadequate public fitness solutions. Outdoor equipment isn't always the greatest, etc. So we felt there was a need for affordable, durable, and adjustable resistance weight training equipment that could fit a variety of needs. So we wanted this to be low cost. Obviously, we wanted it to be weather resistant, so that it could be used outside. And we decided a squat machine would be the best for this, as you could target a rather diverse range of muscles. Alright, so this is our summary of customer requirements and engineering characteristics, what we came up with. So sort of based on the problem statement I mentioned before, this kind of goes along those guidelines. So obviously we wanted it to be affordable, as we mentioned in the problem statement. How do we accomplish this? So we made sure the total cost was less than that of an average gym membership. We wanted it to be usable outdoors, so we made it corrosion resistant by adding acrylic latex. We wanted it to have adjustable resistance. We did accomplish this. We made it adjustable safely from 15 to 135 pounds. We wanted it to be durable and require low maintenance. We used a steel frame. We validated this with FEA. We also, for accessibility, we wanted it to be easy to assemble on your own if you were to do so. So we used a lot of off-the-shelf parts that we could easily source from places like McMaster, and we also included a DIY manual. So obviously safety is paramount. We want it to be safe for the public. Therefore, we designed it in such a way that it was stable, and we do plan to have safety stops designed at some point to prevent it from crashing if someone were to lose their grip or something. And lastly, we wanted it to be ergonomically adaptable. Therefore, we made an adjustable pivot and shoulder rests. So, then that is all for my section. I will go ahead and pass it on to the next person. Thank you for listening.
Hi, I'm Judd, and I'll be doing the design overview. Simply put, the machine is a lever arm with variable resistance. The pivot assembly secures everything to a concrete foundation while also housing the lever arm bearings for smooth operation. The lever arm is a beam which transfers the load to the user via the shoulder rest and restricts motion along a safe path. Finally, a weight can slide along a portion of the lever arm and locks into place in order to change the resistance. Now, to get a better look at things, here's a short video. The two forks are the shoulder rest, where the one on the far end is a Class 2 lever arm and supports between 15 and 45 pounds, while the central shoulder rest is a Class 3 lever arm which supports between 45 and 120 pounds. In either case, the closer the weight is to the far end of the lever arm, the higher the resistance and vice versa. Once a weight has been selected, a user gets under a shoulder rest and squats as they normally would. Now, in terms of benefits, our design is constructed of off-the-shelf materials, which reduces production costs as we don't need custom hardware. Alongside that, using off-the-shelf materials increases accessibility as it can be built almost anywhere. Our design also supports resistances from 15 to 120 pounds, which is crucial as it gives new lifters a place to start while also benefiting intermediates. This also means that new lifters can progress over time as they become stronger. Lastly, our design is constructed using threaded pipe, so machines can be built at scale with minimal training. This also allows us to market the product as a DIY product, which further increases accessibility.
This is Imam Samurai, Group 6, and today I will be covering prototype testing plan. After completing the design phase and validating functionality through simulations, our team is moving into the physical prototype stage of the squat machine. This phase involved building and testing the actual machine to ensure it meets the project specifications. We will source parts locally when possible to minimize costs, with McMaster-Carr as a backup. Feedback from our project sponsor will be incorporated throughout. Testing will follow a structured plan with some tests running in parallel to ensure both efficiency and thorough performance evaluation. Test 1, Performance Test, Force and Motion Verification. This test verifies the squad machine force and motion functionality. We aim to confirm the lever arm supports 15 to 135 lb in both Class 2 and 3 setups. A force gauge will measure loads at different arm positions, while a camera records motion during squats. We'll ensure resistance stays within range, and shoulder rest movement does not exceed 4 inches. The 3-day test includes setup, execution, and analysis. Result will help determine if refinements are needed for optimal machine performance. Test 2, Adaptability Test. Test 2 checks how adjustable the shoulder rest is for users of different sizes. Steel pipes will be modified for position flexibility along the lever arm. Using a 45 lb plate, we'll test the shoulder rest at length of 10, 11, and 12 inches. 3 users with varying body type will perform squat at each settings. Comfort and ease of adjustment will be evaluated. This 3-day test aims to identify the most ergonomic configuration to accommodate a wide user's range. 3. Human acceptance, pivot height testing. This test evaluates pivot height comfort, which is essential to user experience. A PVC lever arm will be used to try different pivot heights while users perform squats. Their feedback gathered by video analysis. This helped determine the optimal height for comfort and performance, although a precise height won't be finalized. This test provides insights for design improvements. Conducted in Spacious Workshop. This test emphasizes user perception and will guide future iteration of the machine design. Test 4, Class 3 lever arm length testing. Building on Test 3, this test determined the most comfortable Class 3 lever arm length, while maintaining a resistance of at least 90 lb. The pivot height will be set based on the previous results. Then the arm length adjusted in 6 inches increments. Users will perform squat at each settings, with comfort rating documented through video analysis. This goal is to balance functionality and comfort. The test spans 4 days covering setup, testing, and analysis to refine arm length. Test 5, Durability Test. Examines the squad machine durability through stress scenarios. 2 main tests will be performed. A drop test where the lever arm is released from its highest point, and misuse test that apply lateral force to key components. These simulate real-world abuse and help evaluate structural reliability. Success is measured by the absence of damage or malfunctions. This 2-day test includes setup and evaluation, ensures the machine can withstand heavy and unintended use over time.
Now, for the results, I need to clarify that despite our best wishes, we ran into some sourcing issues and were only able to do the comfort-related tests. These tests consisted of our 2 participants squatting and rating their comfort on a scale from 1 to 10 for each configuration. We understand that this is not enough to draw significant conclusions, but since they're on opposite ends of the height spectrum, we felt that if they found our design comfortable, then so would the average user. Alongside this, we used video tracking to ensure that the bar path would remain mainly vertical, as this mimics natural movement patterns. For test 2, the goal was to determine the most comfortable width of the shoulder rest. Looking at the trends, we found that the comfort ratings appeared to increase as the width increased to a maximum of 8.6 out of 10 for the 12-inch wide version. We also noticed that despite identical shoulder rests, the Class 2 position scored higher on average, which will be discussed further in future slides. That said, a 12-inch wide shoulder rest was selected for the final version as it scored the best and was the easiest to procure. For test 3, the goal is to find the most comfortable pivot height. We tested a range between 3.5 and 6 feet and found that the 5-foot pivot height to be the most comfortable on average. Now, like the previous test, we found that the Class 2 lever arm scored higher on average and believe this is because a longer lever arm creates a more linear motion. That all said, we selected the 5-foot pivot height for the final design. Now, to back up our claims in test 2, we also analyzed the bar path using video tracking and found similar trends. That is, as the horizontal displacements decreased, the comfort ratings increased, which lines up with our belief that linear motion is more comfortable. Now, considering the 5-foot pivot height produces a maximum of 4.4 inches of horizontal displacement, We are confident in saying that the motion is safe and would be comfortable for most users. Finally, for test 4, the goal is to determine the most comfortable distance to place the central shoulder rest, as it experienced the more horizontal motion and is less comfortable overall. We noticed that comfort ratings increased as the length increased, which once again reinforced our belief that a more linear bar path leads to higher comfort. Now, of the tested lengths, the 4-foot arm produced the highest score on average with 6.5 out of 10. That said, we ended up selecting the 3.5-foot lever arm instead, as it improves upon our initial design of the 3-foot section while minimally affecting the stress response and load rating.
Hello, this is Ty Yemnitz with Archimedes Health, and I'm going to be going over the customer feedback and future work. We'll start with the customer feedback, and really these two are related because all future work is going to come in some way, shape, or form, or at least be guided by customer feedback. So the first priority there is iterating the design based on how the platform is used. So we can break this down into how we intend the platform and the weightlifting machine to work, and how customers actually use it and how they integrate it into their workouts. Understanding how they will actually use it once it gets in their hands is going to be really critical for any future design iterations that might occur. Next one is going to be safety, of course. This has been a priority from the get-go with us, but of course, we're always going to be evaluating how safe the device is, and if there's any possibility to improve the safety, that's going to be a top concern to both us and the customers. So these are things like pinch points. If it does fail, making sure that it fails in a non-critical or a non-structurally critical way. The next step is, and generally speaking for weightlifting devices in general, a 10-year time span for the life tends to be the expectation. So we would want to, at the very minimum, meet that. And that comes down to a couple criteria. One of them being the weathering. This is an outdoor machine. So the conditions, there will be some variation, but in general, going through standard cycles of squatting and returning it back to baseline, we want to make sure that it can withstand up to 10 years of use. The next one will be DIY capable. This is super important because having an open source platform was one of the key ideas when we were developing this. So being able to maintain that vision is going to be important, namely with capable and basic tools that anybody might have at their house. The next section is going to be the future work. Like, where do we go from here? Well, we're still in the very early stages of launching the business. We've submitted the provisional patent application. So, within the next 12 months, we will want to fulfill and actually file a non-provisional patent application to protect and any of the IP that we may be developing here. The next kind of future priority for us can be to improve the DIY guide. Also like to build a full-scale prototype. And then of course, marketing and manufacturing. These are things like actually getting the product to market, identifying what the initial market is that we are going to approach, and then how we will effectively communicate the value that Archimedes Health can deliver to try to capture a percentage of that market. The fitness market is not going away, especially for gym equipment. So it really is just a matter of how much of the market can we capture, and that's going to come down to how much value can we actually convey. The final step being manufacturing. We'd like to partner with a manufacturing partner that can help produce this on more of a mass scale. Thank you for your time.
Hello, this is Sai Joshi with Archimedes Health. I would like to further touch upon customer feedback and future work. First of all, a customer feedback or user feedback is highly crucial for any product to become successful in the market or in the world, as the customer is the only unbiased person, and as this prototype goes into the market as a fully manufactured machine and it will be deployed in the market, it will be exposed to a variety of users with different physical attributes and mentality. So their feedback is highly crucial, and it must be evaluated and changes must be implemented if necessary. Also, safety is of topmost priority. To touch upon what my teammate Yamitz said, as the machine is exposed to the public, a constant improvement and observation regarding safety must be kept to avoid any mishap, as it is available to small kids to elderly citizens as well. Also, if the machine, if our machine is successful in the future, then we must look on to cheaper manufacturing alternatives to cut down the cost significantly. Maybe move the manufacturing to a different country. Also, the DIY kits then can be manufactured in a different country. Yeah. Our immediate next step would be to build the product and deploy it in a well-researched market where the population is high, where the gym population is high, and just as a test installation to install 2-3 machines before moving on to other places, which will help us collect and gather some data and make any final changes to the design. And based on this, then we can propose a business plan to get funding for our project. And also in the future, based on user feedback, we can try to make the machine more creative and efficient by introducing design changes, thus increasing its effectivity and increasing the interest of people to use the machine. Thank you.
The original budget estimate was created very early on in the project lifecycle to justify that the overall cost was feasible. Based on initial brainstorming, the full bill of materials resulted in a cost of $463 to build the entire squat machine. Now obviously this was a very early estimate that evolved over time, with the main driver behind the increase in budget being attributed to the switch from 3/4 inch steel to 1.5 inch steel for the lever arm. This was to ensure a high factor of safety and minimal deflection when used as a Class 3 lever at the maximum load possible observed during simulation by finite element analysis. In order to test the form, fit, and function of the machine, a first test build was created using 1-inch thin-walled PVC. The results were that adjustments had to be made to both the height of the pivot mechanism and the distance between the pivot and the Class 3 shoulder rests. Following this, a second PVC test was built using thick-walled PVC for a higher fidelity test with less deflection, pipe hangers to test various pivot heights, and smaller adjustable sections of PVC to set the distance of the first set of shoulder rests. This test came in under the submitted purchase request by reusing parts from the original build. A second purchase request was submitted to test key elements of the machine with steel to ensure structural integrity and final checks on form and fit. The idea was to test from the pivot mechanism out to the lever arm without building the entire stand to reduce costs. Unfortunately, we ran into sourcing issues and were not able to complete this prototype. The result of all testing was a bill of materials that cost $814 with off-the-shelf parts and low tolerances, requiring little to no manufacturing, just assembly. This cost includes all adjustments to the pipe lengths to reflect the results of the PVC prototypes and alter the height of the pivot mechanism and the placement of the shoulder rests. While 76% higher than our early estimate on build cost, we believe this price to be reasonable compared to the price of other squat machines with less durability and safety.